Hi everyone, it's Miss Gogerty. We are kicking off our very last unit of the school year. So we are in Unit 8. Primarily, we're going to be talking about area and volume, but for today, we are going to have pretty much a big review of some topics that we've covered out throughout the year. So we are focusing on velocity and net change, and we are covering chapters 6.1 to 6.3 within this next unit. Okay, so please make sure you have the video notes and let's dive in. Okay, so today we're going to start off by looking at a theorem that we are really familiar with, and that's the fundamental theorem of calculus, particularly part 1. Let's look at this a little differently though. Okay, we want to really focus in on what does the theorem tell us and what does it mean in a practical sense. So one of the things that we studied when it came down to the fundamental theorem of calculus part 1 is that this integral was canceling with a derivative. So notation matters, and I want you to really pay attention to something here. I've specifically chosen this format to make you think this F and these F's are not the same, okay? So what's going on? This is the derivative of big F, okay? So something just to note here as we're going, right? This is the derivative of the function f. So we could be writing it d dx of f. I could be writing this as f prime, whatever way you want to think of it. But we have a rate of change. So we are integrating a rate of change, okay? Now, what we've also got going on over here, here's our original function. And we are integrating this function over the closed interval from a to b. So what are a and b? Okay. These are our endpoints on our interval. Now, all that's well and good, but let's think about what we're being told then. So ultimately, we are integrating this function f, and we are finding the change from f of b to f of a. So here's our integral piece, right? Which we also know represents area under the curve, okay? And what we've got going on here is the change in f from x equals a to x equals b, okay? Now I'm gonna start highlighting this, change in, right? Whenever we're subtracting two things, aren't we finding the change in their values? So in one aspect, we can look at it as what's the area under the curve in between A and B, all right? But another way we could look at this is what is the change in area under the curve, right? Or more importantly, kind of going further with it of what's our accumulation? What's our displacement? What's the change in the original function from A to B? Okay, so let's see how this is going to help us. Just as I said, looking at it in a little bit of a different light. Okay, in Unit 6, we definitely studied that if you're taking the integral of a derivative, that those two things are going to cancel. And that ultimately, as long as b is greater than a, we don't even have to find the antiderivative of this. We can just jump straight to evaluating f of b minus f of a. Okay, fundamental theorem of calculus was a pretty big deal for us in saving us some time. Think about it, I believe it was Mr. Rosick did that video. She gave you so many key tips that make sure b is greater than a. So then basically you got to think that we are starting at point A, we're going to point B, okay? And then got into just that we don't have to, once again, find the antiderivative, okay? So let's look at these three examples and let's see if we can make some sense of them. So notice WT is the rate of growth of a child in pounds per year. All right, so we have a rate of change. So what does this mean? Okay, now in symbols, which isn't what we're after, but in symbols, I would hope that everybody would feel comfortable using the fundamental theorem of calculus to write this as W of 10 minus W of 5. But what does this mean? What does this part tell us? And there's a specific reason I'm highlighting still in yellow, okay? So this first part, if we go back to the original function, would be the weight of the child at 10 years old. We are subtracting the weight of the child at 5 years old. So what have we found? if we have the weight of the child at 10 years minus the weight of the child at 5 years, we have now found the change in weight. And you need to put units. This is really important, in pounds of the child from t equals 5 to t equals 10 years. And I want to highlight that again. Change in. Okay. How much has the child changed in weight from 5 to 10 years? All right. Let's take a look at the next one. Now it's a little different, but not much. Oil is now leaking from a tank at a rate of R of t gallons per minute. What does the integral of 0 to 120 of R of t dt represent? Now be a little careful on this. 0 to 120 of R of t dt. I hope that you don't just write down that this is R of 120 minus R of 0. Okay? This right here and the integral, I can't be sure that they cancel each other right away. We have to think about it. R of t is still a rate of change, and it's important to see that. Why does it matter that we have a rate of change? Because that means this is the derivative of something, right? This is a rate of change. So I'm going to change it up. 0 to 120, I'm going to call it L of t. Now, why am I calling it L? I don't know, leaking, okay? R of t is the rate at which the oil is leaking. And once again, I know that because it is telling me it is a rate. So what I know then, oops, I don't want that. I have L of 120 minus L of 0. So I'm going back to the original function that represents the leaking. So what is the amount that has leaked at 120 minutes minus how much is leaked at 0 minutes? Okay, so in all, what do we have? We have the change in oil leaked, and that's being measured in gallons. Make sure we're writing that, from t equals 0 to t equals 120 minutes. All right, I'm highlighting this again, the change in. Definitely need you to look at the fundamental theorem of calculus a little differently right now. Okay, still doing the same mechanics, but what is it meaning? All right, the third one, I want you to try this one without me. There's a little twist, and I'm really curious if you can figure out when you read about this honeybee population, this addition of 100 in here, what is it going to do? I'm going to pause the video, and when you come back, the answer is going to be written up here. So try and write out a sentence and see how you do. Okay, so welcome back. Let's see how you did. All right, so let's start off with the part that I'm hoping you were able to follow, 0 to 15 of n prime of t dt. If you were to put this in words, we have the integral of a derivative. So what we've got going on is actually n of 15 minus n of 0. Well, what does that mean? It's the change in the number of bees from t equals 0 to t equals 15 weeks. So how many bees have either increased? Well, I guess it tells us it's increasing. So how many bees have increased within this hive, okay, or this population? Now the new part is 100. Well, what does it mean that they're adding it on? It's the initial number of bees that the population started with. So in this problem, we have the initial number of bees that were in this population. Then we're adding to it the change in the number of bees from 0 to 15 weeks. So in all, what we have in the end is the total number of bees at week 15. So we don't even need to know necessarily what is the equation that n of t, the number of bees, we don't need it. If we know the rate at which they're changing and how many were in the initial population, we'll be able to find the total number of bees at week 15, at week 16, at week 100, whatever the case is, okay? So by looking at the fundamental theorem of calculus, what we are finding is our net change, okay, of whatever it is we want to study, whether it's how much weight somebody is gaining or losing over time, whether it's a population growing or decreasing, or even here's oil leaking, okay? So this is not something new, but we are definitely looking at how is it now interpreted, all right? Now, with a little bit of a manipulation as well, we can change this equation, the fundamental theorem of calculus, into what we can refer to as a future value formula. But I don't even see them as different. Okay, if I add f of a to both sides, we end up with this equation. All right, so what does this actually mean? If you know 2 of the 3 that are in this equation, if you know any 2 pieces of information, you can get the third. So if I know the rate at which something is changing, and I know maybe the initial amount, it doesn't have to be the initial amount, then I can find some future value. Okay, so let's break this down right now and we'll take a closer look at it. So f of a, this is any point, any given information about the function. So in the B problem that we just did, it was the fact that we were told that the population started with 100 bees. So that means at a time of 0, we had 100 bees, right? It was an ordered pair given. What if they would have told us in the problem that after 1 week, there was 108 bees? And maybe that was the information that would have been given here. That would have been fine. I would have put 108 in here, but then I would have said week 1, right, to 15, something along those lines. We'll see some examples coming up, okay? So f of a is any starting value, any point in the function. Okay, now the other part here, this is the change over the interval a to b. Sorry, I should have wrote interval. All right. So if it's our change over the interval from A to B, and we're adding that to some point that was given, or some output, I should say, then f of b is giving us some future value. Okay. Once again, though, as long as we have any 2 of the pieces of information, we can get the third. All right. So this one, just to make sure that you understand or that you see the connection, this was our number 3 example up above. All right. Okay, so let's look at a problem. The rate of change of an object is given by s prime of t is equal to 3t plus sine of t. At t equals 4 seconds, the object is at 15 feet. Find the position of the function at t equals 7 seconds. So what have we been given? We've been told basically that s sub 4 is 15, right? So the position at 4 seconds is 15 feet. And they're asking us at a time of 7 seconds, what's the position? Okay. Well, since they've given us the rate of change, which is sitting right here, we can use this to our benefit and say, well, we know from 4 to 7 seconds, we'd have to, sorry, I was writing the wrong number, s sub 7 minus s sub 4. All right, so think about what we've got here. Here is the accumulation of change. So how is the object moving? All right, so we already know this value. Sorry, not s of 7. We already know this value. We know this is 15. Over here, because we have this equation, we'll be able to evaluate the integral. So we will be able to find s sub 7. So with a little bit of manipulation, s sub 7 is equal to s sub 4, I'm just adding it to the other side, plus the integral of 4 to 7 of 3t plus sine of t dt. All right, so s sub 4 is 15. I can just fill that in. And now the other part, I gotta have to do a little bit of work. Now, sometimes you'll be able to use a calculator and we can just outright plug that into our calculator and let it do the work for us with the fn int. But for right now, let's just practice and make sure that we're good on integrating this. So I should have 3/2 t squared minus cosine of t. And we need to evaluate this from 4 to 7. we're going to have some nasty values with cosine. So we are definitely going to want a calculator at least to plug this in. So I've got 15 plus, let's see, 3/2 times t squared. So that's going to be a 49 minus cosine 7. And then 3/2 times 16 minus cosine 4. Okay. And I plugged this into my calculator before, but basically these two together gave me a 48.092. Check your work out to make sure that you also got that. So 63.092, and we are measuring in feet because they are asking us what would be the position. Okay. Now, this is a good way of using the net change theorem. So think about what we've been asked here. We knew that the position at 4 seconds was already 15 feet. So we're saying let's add 15 feet, because that's how far it went in the first 4 seconds, added to the net change. Okay, so what is my change in this object from 4 to 7 seconds? So ultimately, I'm hoping that you guys can see that this means take the position at 4 seconds, add it to the change in the position from 4 to 7 seconds. Okay. Now, all of this work would still be the same thing as us going back and saying, okay, well, let's take the antiderivative of this. And if I take the antiderivative of this, which is what we did right here, and then calculate s sub 7 minus s sub 4. We could do that, but we can also just kind of look at, instead of redoing all that work, we've got it sitting right here. Okay. So let's move on and let's look at other variations of these questions. Now, big review from chapter 3, which would have been, I believe, unit 3 as well. Okay, I might have gotten that messed up in my head, but I'm pretty sure this was still unit 3 when we talked about position, velocity, displacement, and distance traveled. So the fundamental theorem of calculus is going to come in and help us with this as well. So position, we were just looking at a problem just like this. So we're definitely looking at an object moving along a line, so a straight line. Okay, so velocity, we have learned, is the derivative of position. Now, something else that I just want to remind you of, if v of t is positive versus negative, that tells us about the movement of the object. So if the velocity is positive, then that means the object is moving in a positive direction. And if we're talking about moving along a line, positive directions on a line are right or up. Okay. If the velocity is negative from way back when, that means we have a negative direction. So the object is moving either left or down. So this is just kind of a blast from the past. Okay. Now displacement, look at what they have written out here. Oh, did we just see this? Have we seen this? Okay, we know that velocity is closely related to position. How closely? Velocity is the derivative of position. So we have a rate of change sitting here. So we have a derivative sitting here. That means that the integral and the derivative are going to cancel and get us back to the fundamental theorem of calculus. Okay, more on this in a moment. All right, but distance traveled versus displacement. We saw this on a test not too long ago as well. Distance traveled is your absolute value of velocity. All right. So with those just reminders, let's come down here. When we were in chapter 3 or unit 3, think about it, you didn't know what an integral was at that time. So in order to find velocity and acceleration, we had to go through derivatives. And very rarely did we try to go backwards, right? We had a position, we found its derivative to find the velocity. We had a velocity equation, we found the derivative to find acceleration, and then answered stuff on distance and displacement. Well, the best part now is that because we have a basis of or understanding of integration, we are able to work backwards so we can have a velocity equation and we can find out the total distance something has traveled or the displacement without even needing to find the original function, the original position function, all because of the fundamental theorem of calculus. So think about what this means, and we had it up above, okay? If I have the integral of velocity, okay, or just integrate velocity, then that means that I am integrating a rate of change. The fundamental theorem of calculus will apply. The integral and the derivative are canceling. So if we want to know the net change, here's that change word again, okay? The change in the function, otherwise known as displacement, I can just go straight to S of B, the position at B minus the position at A. Now, why is this displacement? I want you to think about this logically for a second. If I got up and I took 5 steps forward and 4 steps back, what's my net change from where I started to where I ended? 5 steps forward, right? 4 steps back. I'm only 1 step forward compared to where I was at before. So my net change is 1 step forward, okay? Now, if I was asking about total distance, on the other hand, if I walk 5 steps forward and I walk 4 steps back, my total distance is 9. So what happens to this equation if I want total distance? We've seen this before too. Now we need to take an absolute value, okay? So don't forget that total distance always means that we're taking the absolute value of the velocity function, okay? All right, so let's take a look at some examples, okay? Consider an object moving with a certain velocity. When is the object moving in the positive direction? Well, I don't know about you, but it makes a whole lot more sense to me if I graph this, okay? And considering we're only graphing on an interval of 1 to 5 or 0 to 5, this shouldn't be too bad for us to put together. So if you want to grab a calculator, you go for it, but I feel like we can calculate some of these values pretty quickly. If I put 0 in here, I'm going to get out a -4. Okay, so let me make a point there. If I put in 1, I get out 0. If I put in 2, we get out 2. Put that back. If I put in 3, I also get out 2. Oh, so this is good because now I don't have to calculate the other ones. I know I have a parabola. So my parabola is going up somewhere in here. Okay. It's not perfect, but you guys get the idea. All right, so here is my V of t graph. Okay, so when is the object in the positive direction? Well, that means I need V of t to be positive. So that is occurring in between 1 and 4 seconds. Okay, so moving on, find the displacement over the interval. Well, displacement, here it is right up here. Displacement is going to give me the interval from 0 to 5 of my velocity function. Okay, well, my velocity function is -t squared plus 5t minus 4. Okay, so let's integrate it so I can end up, you got to think, I don't know these values. So the only way I can find the net change is I need to actually integrate this. Okay, I can't say equals s sub 5 minus s sub 0 at the moment, not until I actually do this work. So we could grab a calculator for timing, but let's do one of these. And as I said just before, let's just keep practicing. Plus 5/2 t squared minus 4t. And we need to evaluate that from 0 to 5. Okay. So if I evaluate that from 0 to 5, I'm still going to definitely want a calculator. I have -1/3 times 25. Nope, that was a cubed. That was almost bad. So times 125. Let me fix that and make that a little better. Okay. And if you were at home and you watched that mistake and you caught it, nice job. So 5/2 times 25 minus 20. Then I'm going to have -0. So when I did this, I've got approximately 0.833, and that should be meters. Okay. All right. So find the distance traveled. Okay, so now this was displacement. Okay, so the next one is asking you for the distance. So something is going to change. All right, now I'm just going to try to make this a little bit smaller, just to fit it in. Okay, so as I go to my next one, how is the problem going to change now? Find the distance. Well, 0 to 5 of the absolute value of v of x. You got to think all of this below here, okay, and this here, I need to add that up. So basically, if you remember back to the beginning of the year, it's like if we take the absolute value of it, it's making all of this turn positive. So what I'm going to calculate now is all of this region. Okay, and add it up together. Now, because there is an absolute value symbol on here, I would 100% go to my calculator and do this. So I would encourage you right now, go to your calculator, go to math, the FN int button. So that's math 9. Make sure you know how to plug this into your calculator. And I got an answer of 8.1667 meters. Okay. So please, please, please practice this on your calculator. And if you do not get that answer, bring that question to class. Okay. We don't want you having trouble with putting that into your calculator. Okay. So 2 more quick questions, and then we're going to call this. Okay. So example 3, if the acceleration in meters per second squared of an object is modeled by the acceleration and the velocity is at 1/2 second is 2 meters per second, find the velocity at 1.5 seconds. So this one goes back to being very, very similar to our example 1. So they are giving us the information that the velocity at 1/2 is 2. They want to know what is the velocity at 1.5. We don't know. What's more important here is that acceleration, we know, is the derivative of velocity. So make this as short, sweet, to the point as we can. So the integral from 0.5 to 1.5 seconds of acceleration is the exact same thing as the integral of the derivative of velocity. And we know that this is equal to v of 1.5 minus v of 0.5. Now, why am I doing it like this? Because I have one piece of information, I have a second piece of information, and I can just now fill that in. So I'm after v of 1.5. So v of 1.5 is going to equal v of 0.5, right? Add this to the other side. And v of 0.5, okay, plus 0.5 to 1.5 of negative t squared plus cosine t dt. I know that this lovely first number is a 2, and I'm going to tell you, go use your calculator right now and save a little bit of time. I don't want this video getting much longer than it already is. And so when you would put this into your calculator, the net change, okay, so the velocity's change from 0.5 seconds to 1.5 seconds was a negative 0.565. So my final answer should be 1.435. And this is a velocity. So think about my units, meters per second. Okay, that's just a straightforward plug and chug problem. All right. And lastly, a cyclist rides down a long straight road at a velocity in meters per minute, given by the velocity equation, where t is measured in minutes. How far does the cyclist travel in the first 5 minutes, the first 10 minutes, and how far has the cyclist traveled when her velocity is 250 meters per minute? Okay, so first and foremost, I would absolutely encourage all of you to graph this. We're going from 0 to 10. So at 0, Let's plug in. I'm trying to get an equation for V of t. At 0, we should be at 400. At 10, if I plug 10 into the equation, I'm going to have 400 minus 200, so about here. And I missed it, but hopefully you can be forgiving on that a little bit. Let's try one more time, actually. All right, so here's our velocity equation. What's really important to note is that it never went negative. So that would mean that this cyclist is just riding east or riding north one way or the other, has not turned around and gone back at all. Okay, so how far does the cyclist travel in the first 5 minutes? Notice it's saying how far. How far. This is really important for you all to recognize that it doesn't say displacement. So specifically in this problem, we would need the absolute value of the velocity. Now, because the velocity is always positive, in this particular problem, the displacement and the distance are equal. Okay, so let me say that again. The displacement and the total distance are the same because this velocity function never went negative. Okay, that makes things actually a little bit easier for us. Now, that does not always happen, so be careful on that. So this is not a problem where they're giving me different parts. So I just need to integrate from 0 to 5 of the velocity function. So this is a pretty easy question to do by hand. So our velocity function is 400 minus 20t. So that is 400t minus 10t squared. And I need to evaluate it from 0 to 5. So 0 is nice and easy. There's nothing there. So 400 times 5 minus 10 times 25. And I'm getting an answer of 1,750 meters. Okay. So for my next question, how far does the cyclist travel in the first 10 minutes? Now I'm going 0 to 10. Now it's asking for distance. So again, it would be absolute value, but only because the cyclist, or the velocity function, I should say, never went negative, it's going to be equal to 0 to 10 of v of t dt. So the velocity or the displacement is equal to total distance specifically for this problem. So I already have the antiderivative, but now we're being asked to go from 0 to 10. So 400 times 10 minus 10 times, what do we got? 10 squared, so 100. And I'm getting 3,000 meters, which that's logical that the cyclist has gone further. So last question, how far has the cyclist traveled when her velocity is 250 meters per minute? Okay, so they've given us a velocity. We need to find a distance. So how do we use this? Well, we don't know the time when the velocity is 250 meters per minute, but we could find out because we could take our equation and plug in 250 for the velocity. And once we do a little bit of work here, we'll find that t is 7.5 seconds. So how far has the cyclist gone? Well, I need to integrate from 0 to 7.5 now. It's asking total distance, so I'm again going to put absolute value there. On this particular problem, because velocity is always positive, we know it's still going to be the same as the displacement. So I'm going to have 400t minus 10t squared from 0 to 7.5. And when you plug this into your calculator, 2,437.5 meters. Okay. All right. So ladies and gentlemen, we are done with this video. You guys are going to definitely be practicing this a lot more in class. Main thing that you need to be on the lookout for is when do they give you certain pieces of information so that you're able to find a future value. Okay, when you have 2 of the 3 missing parts to the formula. Okay, you guys all have a great day, and we'll see you in class.